Hello everyone, myself Nishant Ranjan from Group-02 and our topic of project is time series analysis of household power consumption across globe. And this is our group. This project will be able to answer how energy requirement changes over time across geography. Our project can basically be divided into 6 steps and they are as follows. Now, our dataset includes the record of electrical consumption for a single household over 4 years. Every minute observation of power consumption within the household from December 2006 to November 2010 has been included in that. It has 7 variables for different date and time. The variables are global reactive power, voltage, global intensity, and submetering 1, 2, 3. Here in our dataset, we have 3 submetering which record the power consumption of different part of the house. This is how our dataset looks, representing each variable in column and every minute records in row. Moving forward for data processing. In the dataset, we have the total active power and power consumed by different part of household, represented by submetering 1, 2 and 3, but these fall short of the total active power. So we introduced a new term called submetering 4. Here we first converted the global active power to watt hours and then subtracted submetering 1, 2 and 3 from it to get the remaining watt hours, represented by submetering 4. Since we had some missing values represented by question marks, we marked all missing value character with a nan value. Our processed dataset looks like this. Now let's have a look at data visualization. We use different type of graph to look for patterns in our dataset over time. First, we created a separate line plot for each of our variables. From the graph, we can see a downward trend in submetering 4. The graph of submetering 3 kept on increasing and it didn't get affected by changing seasons. Changing seasons didn't seem to have an effect on readings of submetering 3, which shows the power consumption in climate control system, as it keeps on increasing without much spikes. The seasonal effect can be seen in the graph of global active power, which shows some periodic fluctuations. Now, let's have a look at the graph of global active power in detail. As evident from the graph, the active power has a downward trend during the summer months and more consumption during the winter months. During the month of August and September, the power consumption is at its lowest across years. For more detail, let's have a look at per month analysis of global active power. From this graph, we can see some consistent patterns of power consumption across days. At the same time, we have some days of minimal consumption in the month of February, April and August. This indicates that the house was unoccupied at those times. Here also we can see maximum power usage during the month of January and December. Now, Samir will proceed further from here.
Thanks, Nishant. Now proceeding further in the section of data visualization, we analyze few more graphs related to the time series data. Now, as we see in this graph, it represents the active power, the separate histogram for each of the 8 variables. The active power, reactive power, intensity and all the submeter power are well skewed and down towards small watt hour or kilowatt values. The distribution of the active power to be bimodal means it shows that it has two mean group of distribution. Now, let's have a look at the distribution of the active power across the years. The distribution across the years looks almost similar. From graph, it is evident that it has two peaks, with one peak around 0.3 kilowatt and another peak around 1.3 kilowatt. And there is a long tail distribution on higher kilowatt values. Also, we see that each of year, the graph shows the similar behavior over 4 years, showing that two peaks every year. Now considering the next histogram below, we plotted the distribution of the active power for each month of the year. The data distribution for each month seems quite similar with quite a few differences. The peaks are shifted up for the colder months due to the more power consumption due to the more uses of the heating devices, and down for the warmer months. The graph itself explains the consumption and how it varies accordingly. Evident. Uh, Going further, we have also plotted the graph of mean of global active power resembled over a quarter. Also, we have reassembled the data over weeks and computed mean for each variable as shown in the graph. Now, coming to the data statistics part, we know that the data stats consist of the terms like mean, median, mode, count, variance, deviation, quantile, or other related terms. Here we have computed all the terms like mean, median, mode, standard deviation, min, max, etc. This Here we have computed the median and mode for each of the variable of the given data. Now for the hypothesis testing part. In hypothesis testing, we have to check that whether the mean of the global active power will increase or not. In this, first we assume a two hypothesis. Null hypothesis is that the mean will not increase, and the alternative hypothesis is that the mean will increase. Now we used z-test for the testing part, and we used z-test specifically because our data set was too big. And from analyzing data statistics, we already knew the variance of the data set. After finally implementing the z-test, we got the final result that mean will increase. Now I would like to invite Shivam Krishna to take on from here on. Thank you.
Thanks, Samir. Now we will discuss about our prediction model. With the recent increase in the smart meters across the residential sectors, we have large publicly available data set. With such data, the power consumption of individual households can be tracked in almost real time. Such prediction can help power companies to regulate their supply, and also the consumer can use this information to make the better decision both financially and environment consciously. So for this we will do predictive modeling. Basically it is a statistical technique using machine learning and data mining that helps in predicting and forecasting likely future outcomes with the aid of historical and existing data. For this project, we addressed this challenge by trying three different machine learning algorithms since we have the structured data. It helps in establishing correlation in exceptionally large data set and to learn and identify the patterns within the data. And we will also do a comparative analysis to see which approach works best. The three approaches used are linear regression, random forest, support vector regression. Since our dataset is very large and we require a good estimate of model performance quickly, we will incur the train test split procedure. This procedure involves taking a dataset and dividing it into two subsets. The first subset is used to fit the model and is referred to as the training dataset. The second subset is not used to train the model. Instead, the input element of the dataset is provided to the model, then predictions are made and compared to the expected value. This second dataset is referred to as the test dataset. The scikit-learn Python machine learning library provides an implementation of the train test split evaluation procedure by train test split function. In this, one main configuration parameter is the size of train and test sets. This is most commonly expressed as a percentage between 0 and 1, and for either train or test data sets. And it depends upon the computational cost in training and evaluating this model. Here we used 20% of the dataset as a test dataset and 80% as train dataset. Another parameter we used is the random state, which controls the shuffling applied to the data before applying the split. Specifying it any integer means no matter how many times you execute your code, the result would be the same. That is same value in train and test dataset. Now we will do comparative analysis. For comparative analysis, we will see R square parameter and RMSE parameter. R squared is an statistical measure that represents the proportion of the variance for a dependent variable that is explained by the independent variable or variable in the regression model. So if the R square of a model is 0.50, then approximately half of the observed variation can be explained by the model's input. Now for RMSE, RMSE is an statistical modeling and particularly a regression analysis that is a common way of measuring the quality of the fit of the model. Okay, so RMSE is concerned with the deviation from the true value. So lesser the value is, more the fit the model it is.
Thank you, Shivam. For our project, we use linear regression model to fit a line in the data. If the target function is linear in nature, linear regression is fast with little correlation among the features. The issue with linear regression is it's sometimes too simple of a model to fit complicated real-world data properly. So we use this model first because his model has been used have a baseline performance with a simple model before going on with more complicated ones. So we choose global active power as the target variable and we obtain R square value, which implies that how close the data are fitted in regression line, and the value is coming like 0.8709, which is good and implies how our independent variable explaining the variation of dependent variable. So now we obtain only R square value which fit the model with relative measure. So we obtain RMSE value which indicate the absolute fit model to the data and how close the observed data points are to the model predicted values. And the value of RMSE is coming like 0.11907. And finally we obtain a scatter graph of linear regression model of absolute global active power versus predicted global active power, which we see that points of the data are fitted properly and see that actual and prediction are very close. So now overturn to Yash.
Thanks, Rahul. Now, we implemented random forest algorithm to generate our second prediction model of the project. The random forest algorithm is based on a decision tree. In this method, we take random samples from total dataset with replacement. Each random sample is then fitted to a decision tree, and finally, for getting the output, we aggregate the result for each decision tree to get a single result. In this method, if the number of trees in the forest increases, the processing will take more time, but we will get more accuracy. For writing the code, we first imported the random forest aggregator from sklearn.ensemble library and also mean squared error and R2 score from sklearn.metrics library. For our model, we took the maximum depth to 50 and number of trees 200. Also, we kept the random state equal to 0. So, after all this, the R2 parameter finally came to be near 0.999 and the RMSE value was near to 0.009. And finally, after fully implementing, we finally tried to plot the RMSE and it looked like this. Now, Anand will explain you about the last regression model in the further video.
Thanks, yes. We will predict the variable global active power by the support vector regression, abbreviated as SVR model. Support vector regression is a supervised learning algorithm used to predict discrete values. SVR uses the same principle as the support vector machine, abbreviated as SVM. The basic idea behind SVR is to find the best fit line. In SVR, the best fit line is the hyperplane that has the maximum number of points. Here, in SVR, we use the margin same as SVM. This margin around the target hyperplane signifies the amount of error that is tolerable in prediction. The matrix value based on the dataset by using the SVR model is shown on the slide. The R-square value is 0.685 and the RMSE is 0.198. In our project, we did the prediction through three regression models that are linear regression, random forest regression and support vector regression. So this was the comparative analysis we have done with all the models, and the table below shows us this comparison in a better way. Since we saw that the maximum R square and the minimum RMSE value are for random forest regression, so we will predict using a random forest regression model. Here we use time data as well as some metering data consideration. So in a model we predicted the total power consumed based on these data. Here we have shown the variation of the R square value with depth for the training and validation dataset respectively. Similarly, in this slide we have shown the plot for variation of RMSE value with depth for the training and validation dataset respectively. Now we will look the conclusion part. We can observe that the R square value for the validation set is substantially lower at roughly 0.48 and the model begins to overfit beyond a maximum depth of 4000. With average global power in the data about 65.5 kW, this RMSE is about 60% of the mean power in case of only time data. Overall, we saw that this model is great in predicting total wasted power when metered power is known, with an R square value of about 0.99 with RMSE value 0.009 with random forest regression. Thanks, and here we end our presentation.